This video today is going to be about electric fields due to point charges, systems of point charges, and then we'll also talk about continuous charge distributions, and then eventually we will be talking about electric flux and Gauss's theorem. Now, to start with, we will briefly review what we learned in the previous video, and that was the field due to a given point charge. Now, if we have a point charge now we have here a point charge. Now let's say this is plus, the point charge has a magnitude of charge q here, and we are interested in calculating its electric field at a distance r from it. Now its electric field at a distance r will be pointing away from the charge and will have a magnitude 1 by 4 pi epsilon naught q by r square, where r is this distance. Now this field will be directed radially away from the charge. So this field, I have given this electric field vector. I've shown the electric field vector here. This electric field vector has this magnitude, and the direction is always away from this positive point charge. Now, if in place of a positive point charge we have a negative point charge, and we are interested in finding the electric field at a distance r from it, say this distance is r, and we are finding the electric field over here. Now here the electric field vector will be directed towards the charge. So this is the electric field directed towards the charge, and the magnitude, of course, is still the same, 1 by 4 pi epsilon naught q by r square. Of course, these are results for the net electric field in vacuum. If in place of vacuum we had some material medium, then in place of epsilon naught we'll have epsilon naught times epsilon r. These are the electric fields due to individual point charges. Now, if in place of two individual point charges we have a larger number of charges, then at a given point, if the electric field due to a charge in its neighborhood is E1, due to another charge it is E2, and so on and so forth. There are lots of charges, let's say, and they all produce their own electric fields, E1, E2, E3, and so on, all the way up to En. Then the net electric field at this point is the vector sum of E1, E2, E3, and so on and so forth, all the way up to En. This is, of course, our superposition principle, and here the individual electric fields due to individual charges are due to those individual charges alone. The electric field due to a given charge is not affected by the presence or absence of other charges in that neighborhood. So this here is a brief summary of what we learned in our previous video. We will now move on and discuss electric fields due to combinations of charges. Now, one very simple and very common combination of charge is what we call an electric dipole. Now, what's an electric dipole? An electric dipole is a pair of equal and opposite point charges separated by a usually small fixed distance. So if we have a pair of charges, equal and opposite pair of charges separated by some distance which is fixed, then we have a dipole. Usually, as I said, the distance between these two equal and opposite charges is a small distance, and why it is small? Because most of the times, most of the dipoles that we are accustomed to in our lives come from molecules, and in molecules where you have some charge separation, some ionic character, the positive and the negative charges are separated by very tiny distances. Molecules are not like in kilometers, they're very tiny, and the interatomic distances in a molecule are typically of the order of angstroms, which is 10 to the power minus 10 meter, and therefore the distances between the two charges that we're talking about in a given dipole, those distances are very tiny distances. Now if we have a pair of equal and opposite charges, minus q and plus q, separated by a small distance, let's say a, then we have a dipole on our hands. Now a dipole has a physical quantity associated with it. We define a physical quantity which kind of measures the magnitude of this dipole, and that physical quantity is called the electric dipole moment. So the physical quantity associated with an electric dipole is called an electric dipole moment, and it is represented by a vector quantity P. Now this vector quantity P, called the electric dipole moment, is given by the magnitude of one of these charges times the distance between them, and it is directed, this A vector here has the same magnitude as this distance A, and it is directed from the negative charge towards the positive charge. So the direction of A vector and the P vector is same, from the negative charge towards the positive charge. So that is the electric dipole moment for a pair of equal and opposite charges. This electric dipole moment, remember, is a vector quantity, and its unit would be Coulomb meter. It's also given a name sometimes, and that name is dBi, but well, we need not really bother too much about it. Coulomb meter works fine enough. So we've defined the electric dipole moment for a pair of equal and opposite charges. If we have a large combination of charges, and in that system of charges the number of the total negative charge equals the total positive charge, then we can always define a dipole moment for that combination. How this can be done is, we just break the system up into lots and lots of pairs of equal and opposite charges, or distinct pairs, no charges should be repeated, and then for all those pairs we calculate the dipole moments using this result. and then add them all vectorially to get the net dipole moment for the entire system. I can give you a simple example here where we have a system of actually 3 charges. We have, say, a charge minus 2q here, and we have 2 other charges plus q each, and all 3 of them lie on the vertices of an equilateral triangle of side A. All 3 of them lie on the vertices of an equilateral triangle of side A. Now what we can do pretty easily is divide this minus 2q into 2 point charges minus q each. So this one's minus q, the other one is also minus q, so it's still minus 2q. And now we have 2 pairs of equal and opposite charges, minus q and minus q and plus q here. These 2 pairs of charges constitute 2 different dipoles. This one having a dipole moment P given by QA, that's the magnitude of this dipole moment vector, and it's directed from the negative charge towards the positive charge. The other one has the same magnitude, actually, Q times A, because the charges are same, the distance between them is same. But now this one is directed this way, in the direction from this negative charge towards this positive charge. So we have 2 dipoles, each of magnitude P, a dipole moment P. The angle between them is 60 degrees. Now the resultant of these 2, when added vectorially, should give us root 3 times P. Quite easy to make that calculation. P resultant or P net should be equal to P square plus 2P into P into cosine of the angle 60 degrees between them. And so this is 2P square plus 2P square times half, and that's root 3P. And because of the symmetry here, the angle here is 60 degrees and these 2 are equal, and we have a parallelogram with a perfect parallelogram with these 2 sides being equal. This angle will be 30 degrees. Of course, if you are fairly conversant with vector addition, you can confirm this 30 degrees. And so the resultant dipole moment here is root 3 times QA. So that's an electric dipole. We've now defined an electric dipole. What we will now be doing is we will be calculating the electric field due to an electric dipole. Now to do this, we have to define a couple of interesting little ideas, and that is the dipole axis and the dipole equator. Now in a dipole, if this is minus q and this is plus q, then the line joining the 2 charges, this line, is called the dipole axis, and the perpendicular bisector of the dipole axis is called the equatorial line. What we are going to try doing is, we'll calculate first the electric field due to a dipole on the dipole axis and then on the equatorial axis, and then we'll look for a general kind of a point for calculating the electric field. So now that we are clear about dipole axis and the equatorial line, let's start discussing the electric field due to a dipole at a point on the dipole axis first. So let's consider a dipole having a charge minus q and a charge plus q, separated by a distance a, like I have shown here. So this is minus q, this is plus q, and the distance between them is a. Now this line here is the dipole axis, and we are going to calculate the electric field here at a distance r from the midpoint of the dipole. So this is a point on the axis of the dipole or on the axial line of the dipole, and we are finding the electric field here. Now let's say at this point the field due to the positive charge is E plus. Now this E plus has to be directed away from this positive charge, as we just discussed some time back. Now at the same point, the electric field due to minus q will be directed towards minus q because it's a negative charge. Let's call this E minus. Now we are quite easily capable of guessing that E plus is greater than E minus. Even though the charges are equal, the distance of this point from the positive charge is less, and the distance of the point from the negative charge is greater, and we know that electric field is inversely proportional to the square of distance from a charge, and therefore the electric field due to the positive charge is greater than the electric field due to the negative charge. The net electric field over here will therefore be directed parallel to E plus. That's your net field, and this net field will have a magnitude equal to E plus minus the magnitude of E minus. So one conclusion that we have arrived at already is that the net electric field due to a dipole at a point on the axial line is directed parallel to the dipole moment, right? So now what we figured out that the electric field at a point on the axial line of a dipole is directed radially, directed along the direction of the dipole moment. Whether the point is on this side or on this side, the net electric field will always be directed parallel to the dipole moment. Now at this point we are interested in calculating the net electric field due to this dipole. Now this net electric field we know is E plus minus E minus, and therefore we have to now calculate E plus and E minus. E plus, of course, is 1 by 4 pi epsilon naught times q by the square of this distance. Now the square of this distance will be r minus a by 2 whole square. This distance here is r minus half the length of the dipole, that's a by 2. So square of the distance, r minus a by 2 over here. This is E plus, and then E minus is 1 by 4 pi epsilon naught q by the square of this distance now. Now this distance is r plus a by 2, and therefore we now have r plus a by 2 whole square, and therefore now the net field is going to be E plus minus E minus, and that's q by 4 pi epsilon naught into 1 by r minus a by 2 whole square minus 1 by r plus a by 2 whole square, and therefore the net field is q by 4 pi epsilon naught. In the denominator we'll have r square minus a square by 4 whole square, and in the numerator we have r square plus a square by 4 plus 2ar plus ar minus r square minus a square by 4 plus ar. So after some cancellations, this r square cancels, a square by 4 cancels, and you're left with 2ar in the numerator there. So net field is 1 by 4 pi epsilon naught q a r times 2 by r square minus a square by 4 whole square. Now this QA is the dipole moment, so E net is equal to 1 by 4 pi epsilon naught 2 times QA, which is P, and since the directions of net field and the dipole moment are same, we can use a vector sign here. Now in the denominator we have r square minus a square by 4 whole square, and we are still left with this r over here. Now more often than not r is very large compared with a. You will recall our definition of the dipole, which says dipoles are usually small, so this a is very likely to be very small in comparison to r. A is very small in comparison to r, and therefore a square by 4 here is negligible in comparison to r square. And so what we have is net field equals 1 by 4 pi epsilon naught 2p r by r square to the power 2, that's r to the power 4, and therefore one of these r's cancel out and we are left with r cube here. More often than not it's this result we use because dipoles are typically small. If you are dealing with larger dipoles, then you will end up using this result, but as I said, dipoles are generally very, very tiny, and therefore a square by 4 here is always negligible in comparison to r square, and we end up with this result. So this then is the electric field due to a dipole at a point on the dipole axis. We now move on and take up calculation of the electric field on the equatorial line of a dipole. So let us again consider a dipole having two charges, minus q and plus q, just like in the previous case. So we have plus q we have minus q, and the distance between them is A. Now, of course, the dipole moment of this thing is q times A, and now this line here is the equatorial line. Now, at a distance x on the equatorial line, we have a point here where we are interested in calculating the electric field. Now, this is a by 2 and this is a by 2 as well, and this distance is x. Therefore, this length here will be root of x square plus a square by 4, and this length as well, same, root of x square plus a square by 4. If we take this angle here to be theta, then this will also be theta, and you can easily take calculate the values of sine theta and cos theta from here. For instance, cos theta will be x divided by root of x square plus a square by 4, and similarly you can calculate sine theta, it would be a by 2 divided by this length here. So this then is the situation. We are finding field due to a dipole on the equatorial line. Now, at this point, the electric field due to plus q, field here due to plus q will be directed away from plus q this way. Let's call it E. Now this E will have a certain magnitude, we'll calculate it, and then we have this minus q. This also produces an electric field. Now this time the electric field is directed towards the charge, and it has the same magnitude E. Now why the magnitudes of these two fields are same? Because the magnitudes of the charges is same, their distances are also same. There is therefore therefore is the reason for the fields being same. Distances are same, charges have the same magnitude, so fields have the same magnitude. The only thing that differs is the direction, because they are located differently and they have different signs. Now this angle here is theta, and so is this. Now if you were to take components of the electric field here in x and y directions, what you will get is E cos theta here and E cos theta here as well. These two components, E cos theta each, which are along this equatorial line, they are equal and opposite. Now we are all aware that the sum of equal and opposite vectors is 0, so these two cancel each other out. The other components of E, which are perpendicular to this equatorial line this way, now both these components will be E sine theta each, and these two are in the same direction. Now this will be the direction of the net electric field here. This is the net electric field, and this net electric field will be 2E sine theta. Now remember that E is the electric field due to one of these individual charges at this point, magnitude of the field, and sine theta is the sine of this angle here. We already know cos, sine theta of course would be equal to a by 2 divided by this length, which is root x square plus a square by 4. So we now calculate this E net. It equals to E. E of course will be 1 by 4 pi epsilon naught magnitude of the charge divided by the square of this distance here. Now this distance when squared gives you x square plus a square by 4, and then you multiply this E 2E by sine theta. How much is sine theta? Well, we have sine theta here, a by 2 divided by root of x square plus a square by 4. So this net electric field comes out to be 1 by 4 pi epsilon naught. This 2 and this 2 will cancel out. We have QA, that's your P, divided by x square plus a square by 4 raised to the power 3 by 2. See, this power here is 1 and the power here is half, and when you multiply two quantities, their powers are added, 1 and half when added give you 3 by 2. So this is the dipole moment P, and therefore the net electric field will be equal to 1 by 4 pi epsilon naught P by x square plus a square by 4 raised to the power 3 by 2. Now as I said, typically dipoles are very small, and therefore A would be very small in comparison to x, which would mean that a square by 4 is negligible in comparison with x square. So we neglect this a square by 4, and the net electric field now comes out to be 1 by 4 pi epsilon naught P by x cube. The direction of the net field is opposite to the direction of the dipole moment P. You will notice here that the dipole moment is directed upward and the net field is directed downward. So they are opposite in direction, and so if you were to use vectors, vector signs here, you have to have a minus. This minus indicates that the directions of the net field and the dipole moment are opposite. So this then is the formula for the electric field due to an electric dipole at a point on the equatorial line. On the equatorial line, the net field is directed opposite to the dipole moment, whereas on the axial line it is directed along the direction of the dipole moment. Now we've seen the electric fields due to a dipole on the axial line and the equatorial line. Let's now try some arbitrary point, some point which does not lie either on the axial line or on the equatorial line. Now let's say we have a dipole here, this is the dipole, and we are going to find the electric field at a point distant r from it, and this r vector is at an angle theta with the p vector, p being the dipole moment. So we are finding electric field into a dipole at an arbitrary point. Now, by an arbitrary point, what I mean to say is it's not some special kind of a point like on the axial line or on the equatorial line. It's some arbitrary point. So it lies neither on the axial line nor on the equatorial line. The value of r is very large compared with the length of the dipole, which is typical. Now, to calculate the electric field here, what I'll be doing is I'll resolve this dipole into its two components. One component is the one that's directed along r. Now this component will be p cos theta, and the other one is p sin theta. Now p sin theta is perpendicular to r and p cos theta is directed along with r. So now in place of one dipole I have two dipoles. What I will do is calculate the electric fields due to these two dipoles at this point. I'll be calculating their fields. See, I have broken this up into two dipoles. I'll be calculating the electric fields due to these two dipoles separately. Now, the net electric field at the point will be a vector sum of the electric fields due to these two. So this vector is made up of these two vectors. I am calculating the electric field due to this one at this point and the electric field due to this p cos theta at this point. I will then add those electric fields vectorially and get to the resultant value of the electric field at the point. Now, the electric field due to this dipole p cos theta, let's call this 1 and let's call this 2. The electric field due to p cos theta here will be, let's say, E2. Now this E2 is on the axial line for p cos theta. It's on the axial line. On the axial line, the electric field is directed along the direction of the dipole. So it's directed along the direction of the dipole, and it equals 1 by 4 pi epsilon naught 2p. Now in place of p I have p cos theta by r cube, right? This is really E1 because it's due to 1, so let's call it E1. I will call it E1 here as well. So E1 is the electric field due to dipole 1. Due to dipole 2, we have an electric field over here. We'll call it E2. Now try and make a guess about the direction of E2 here. As far as the second dipole p sin theta is concerned, this point is on the equatorial line. Now on the equatorial line, the electric field is directed perpendicular to the equatorial line and opposite to the dipole moment. This here is E2. So E2 is perpendicular to this line and opposite to the dipole moment. This E2 therefore is 1 by 4 pi epsilon naught. Remember, it was p by r cube, but now in place of p we have p sin theta by r cube. Now the net electric field at this location will be the vector sum of E1 and E2. So this here will be E net, this vector, and it will make an angle phi with this radial line. Now this magnitude is E1, and this magnitude here, this E2, is obviously equal to this line. So this is E2, this is E1. We can easily calculate tan phi. This tan phi will be having a magnitude equal to E2 by E1. Now look over here. If you divide E2 by E1, what do we get? We divide E2 by E1, we get half of tan theta. So the direction of this net electric field, is given by, this angle phi is given by tan phi equals half tan theta. That's the first information we get. Also, we can easily calculate this net electric field in terms of its magnitude. This net electric field will have a magnitude equaling the under root of E1 square plus E2 square. Now you substitute these magnitudes and the net electric field comes out to be, I'm skipping the calculations, pretty sure you can manage them yourself. And so we have over here P by R cube times root of 1 plus 3 cos square theta. So that's the magnitude of the field, and the direction is given by this rule here. This is the electric field due to a dipole at some arbitrary point. Now about dipoles and about electromagnetism, there is something very, very interesting that we can now discover, and that is that in electromagnetism, the third law, Newton's third law, is followed in a kind of weak form. Now what is that weak form of Newton's third law of motion? Let me share this simple example where we highlight the weak form of Newton's third law. Now think of a dipole here. Now this dipole has a dipole moment P, and we place a charged particle at a distance r from it over here. So we have a charged particle placed here. Let's say it's plus positive Q. We are interested in calculating the electric force on both of them. Now, to calculate this electric force on both of them, which they exert on each other, what we do is, well, this P has an electric field at this point directed towards left. Now that electric field is 1 by 4 pi epsilon naught 2p by r cube, right? That's the formula. Not 2p, it will be p by r cube, directed opposite to the dipole moment. Now you multiply this field by the positive charge, you get the force. So force on plus q due to the dipole is towards left. Now Newton's third law kind of still holds. The force on this dipole due to this charge will be equal and opposite. This is the force on the charge due to the dipole. The force on the dipole due to the charge is still equal and opposite. it will have the same moment, magnitude, but what we'll notice here is that these two forces do not have the same line of action. One of these forces has this line of action and the other one has this line of action. So the lines of action of the two action-reaction forces are different. Let's say this force is an action and this force here is its reaction. What we notice is action and reaction forces have different lines of action. Unlike mechanics, this is completely unlike mechanics. In mechanics, now this is what you will find in electromagnetism. In mechanics, if there are two objects A and B exerting forces on each other, let's assume for simplicity that the forces are forces of gravity. If they're exerting gravity force on each other, this is the line joining them, and if they're exerting gravitational forces on each other, then those forces will invariably have the same line of action. So here this is action, this is the reaction, this is your action-reaction pair formed by the forces of gravity. These action-reaction forces action-reaction pair of forces have the same line of action. Now this is called the weak form of Newton's, this is called the strong form of Newton's third law, whereas this form is called the weak form of Newton's third law. So Newton's third law has a strong form and a weak form. Mechanics, in mechanics we have the strong form where the action and reaction pair of forces have the same line of action, whereas in electromagnetism we have a weak form of third law, because now the action and reaction pair can have different lines of action. This never happens in mechanics. So that then is Newton's third law, sort of the additional information on the third law here. Remember therefore that in electromagnetism it's the weak form of third law that is followed, and we move on now to the more complicated cases of calculation of electric fields. We have so far discussed fields due to point charges, and we have discussed fields due to dipoles where we have two equal and opposite charges. Let's now take up a case where we calculate the electric field due to let's say a larger number of charged particles. Let's say we have a square now, the square has a side A, and at the vertices of this square we place charges minus Q, plus Q, plus Q, and again over here minus Q. Now we are interested in calculating the electric field at the midpoint of the square. Now at the midpoint of the square, if we are first, we have to calculate the distances. Now this is A and this is A as well, so a diagonal of the square would be root 2A, and half of that diagonal would be, half of root 2A would be A by root 2. So this distance is A by root 2. Similarly, this distance would also be A by root 2, and then the same here and here as well. So this distance is A by root 2, A by root 2, A by root 2, and A by root 2. At this point now, we'll be calculating the electric fields due to all the individual charges, and then we'll be doing a vector summation. Now the field due to a charge of magnitude Q at a point distant A by root 2 from it, E would be equal to 1 by 4 pi epsilon naught times Q divided by the square of A by root 2, that's A square by 2, and we get this. So at the center of the square we actually have 4 different fields each having a magnitude E. The field due to this plus Q would be directed this way, let's say E. The field due to this minus Q would also be directed this way and would also have the same magnitude. Then think of this plus Q. We've considered the fields due to these two already. Let's talk about this one and this one. The field due to this plus Q is directed this way, away from it, and the field due to this minus Q is also directed towards minus Q, that is in the same direction as the field due to this plus Q. So we have 2E and 2E, both directed at a right angle to each other, and since these 2E and 2E are already known to us, their resultant will be towards the right. This is the net field, and of course this net field will be equal to the root of, now see, this is 2E and this is 2E and they are perpendicular to each other. So 2E whole square plus 2E whole square, and the net field would now be, we take this 2 common and out, so 2 square taken out becomes 2, and we have E square plus E square, and we therefore get net field equals 2 root 2 times E, and E is already known to us here, and therefore this net field comes out to be 2 root 2 times 2Q. So we have this in the numerator by 4 pi epsilon naught A square. The net field therefore finally is 4 root 2 Q by 4 pi epsilon naught A square. If you have a larger number of charges, then you might have to resolve those vectors along x and y directions and then add up those vectors in the analytical form, but questions like those are rarely asked because they kind of get very, very long and lengthy, and aren't really very practical. Such long questions are better solved with the help of calculators and computers, which we are not generally allowed to use in our Indian exams. In any case, the process is known to us, and therefore we can easily calculate those kinds of electric fields. So this then was the information on the calculations of electric fields in case of point charges and systems of point charges. In our next video, we are going to discuss electric fields due to continuous distributions of charge. Thank you very much for watching this video. Bye-bye till we meet again.